Well, here it is, the last of the review sessions. Last of the videos, at least. And I'm on the last chapter in the book and the last topic in Math 104, so I guess everything's coming together. One thing that did not come together is that at the end of last time when I did separable differential equations, I did in fact stumble suspecting that I had made a mistake in my book, and it is true. I did. So for the sake of errata, I wish I could change the book, but I can't. It's already out there. Page 646 and 647. The example should have been dy dx minus, minus cosine squared y cosine x equals 0, not plus. And it also appears at the bottom of page 647 as well. And somehow I integrated minus cosine x and said that it's sine x. And of course, that is the elementary mistake I tell everyone to avoid. And somehow I managed to do it quite blatantly. So all the corrections, it should be the integral of cosine x dx is sine x plus c. And this is not minus cosine x. So there's a correction. If you're watching or in the room, sorry about that. Anyone finding any mistakes, just email me, adrian@calclifesaver.com, and I will be grateful. May even send a free copy of the book to anyone who finds a mistake. Okay, that doesn't count because I just told you. All right, so that was a little tie over from last week. Now I'd like to continue with linear first order. So last time we did separable differential equations. That's one of the three types that we're considering. Okay, so a different type is called linear first order, or first order linear. Okay, what did first order mean? It means that there's only first derivatives around. There's no second, third derivatives, nothing higher than a first derivative. And linear actually means that you can express the differential equation like this. dy dx plus p of x times y is equal to q of x. And the important thing is that this is basically x stuff only. No y's involved in there. And the same with this term. All of the x stuff is isolated. It doesn't look particularly linear. Here's an example. dy dx plus 6x squared y is equal to e to the minus 2x cubed sine x. It doesn't look linear. There's exponentials, there's trigs, there's a quadratic there. How is it linear? Well, it's linear in y and dy dx, where the coefficients are functions of x. So in this case, it's 1 dy dx plus some stuff times y equals some stuff. But the stuff is only in terms of x. So this is an example of a first-order linear equation. Now, this form, you may have to manipulate the equation to get it into that form. And I'll show you an example of that in a little while. Why is it linear again is the question. The answer is that it's just dy dx plus something times y. So it's like a linear function in dy dx and in y, where the coefficients are functions of x. Right? So I'll tell you why it would not be linear. If you had dy dx squared, or some function of dy dx, that would be bad. Also, if you had, instead of a y here, if you had y squared, or sine y, or anything that's not just y, that would be bad. So it's the y and the dy dx stuff that has to be very simple. But the coefficients can be functions of x, which are nonlinear. Okay, so when I say linear, I mean in y and dy dx. All right? Okay, so let me show you how to go about solving this without just doing the general method yet. Let's suppose that I put the e to the 2x cubed on the other side. So I'm going to make it apparently look more complicated. Okay? I just want to show you the idea, and then I'll show you how to think of it. It's not obvious how to think of this. Let's suppose I have the idea of doing this. Now, the amazing thing is that the left-hand side factors. And this is an unusual sort of factoring. It's not an algebraic factor, it's sort of a calculus factoring. Check this out. I'm going to claim that the left-hand side can be factored into d dx of e to the 2x cubed times y. And the right-hand side is still sine x. That's a sort of major rabbit out of the hat. Do you believe it? Let's check it out. How would you differentiate this product? Well, you have to differentiate it implicitly. It's u dv dx. Well, in this case, u is e to the 2x cubed and v is y. So you're going to get e to the 2x cubed dy dx. That's the first term. The other term is y times the derivative of e to the 2x cubed. So that's y. And when you differentiate e to the 2x cubed, you get e to the 2x cubed times the derivative of 2x cubed, which is 6x squared. Amazing. If you use the product rule on this, you get this. The tricky thing is we've done it in reverse. We've done the reverse implicit differentiation product rule. Pretty nice. Pretty nice. Okay, so what I want you to do, if you don't see it already, is later on just convince yourself that this leads to this. Don't worry about how you could possibly see that you can get the other way for the moment. We'll look at that in a little bit. All right, so what's the point of this? Well, if you integrate both sides with respect to dx, then on this side, the derivative just cancels out with the integral, and you just get e to the 2x cubed times y. Whereas on the right-hand side, you have to integrate sine x dx. Well, of course, this is negative cosine x plus a constant. And you don't know what the constant is. Well, now we can just divide again by e to the 2x cubed to isolate y. And y is equal to negative e to the minus 2x cubed cosine x plus c e to the minus 2x cubed. You could factor out the 2x, e to the minus 2x cubed if you like. But it's not just a plus c. In this case, c is outside of something else. And this is true for any constant c. And you could check by differentiating that it does satisfy the original differential equation. I'm not going to do that, but it's not a bad exercise. Find dy dx and see if dy dx plus 6x squared times y, where you plug in that y again, boils down to e to the minus 2x cubed sine x. All right, so there's the solution. There's a major step missing, or not really a step, but there's a major intuition or insight missing. How did I know to multiply by e to the 2x cubed? Well, I'm going to talk about this in a second. Does anyone have any questions about, other than how did I know how to do that one step? Once I've done that step, can you all see how each thing follows to the next step? Are you all happy with that? All right. So, here is the general idea. If you have an equation that you can rearrange into this general form, dy dx plus p of x times y equals q of x. What you do is you grab this little object here, p of x, so that's the x stuff sitting outside of the y, and you form what's called an integrating factor. And here's how you do it. You take the integral of p of x, dx, but you raise e to that power. And actually, you don't need a plus c. It doesn't hurt, but you don't need it. You might as well. Might as well omit it. So that's the integrating factor. If you multiply through the differential equation, so the first thing you do, multiply the original equation by this integrating factor. So you do that first. And then the left-hand side factors, hence the integrating factor, the left-hand side factors into d dx of the integrating factor times y. And from then, it's fairly straightforward. Then just integrate both sides. And solve for y. You have to divide by the integrating factor to do that. Okay, I haven't said why this works, but at least this should give us some insight into how I knew to do what I did before. So let's go over to this problem here, and let's cover up the bottom, and just look at this equation here. What's the integrating factor? Well, the integrating factor equals e to the power of the integral, and I take this 6x squared here, and I stick that up here. But I have to integrate it. Well, the integral of 6x squared is actually 2x cubed. I don't need the plus c. I just integrate 6x squared, 3 divided by 3, 2x cubed. And that's the integrating factor. And that is exactly what I multiplied through. We can now reveal it in this step. Right? E to the 2x cubed, e to the 2x cubed. It coincidentally canceled out the e to the minus 2x cubed, which was nice, because otherwise we would have had a nasty integral on the right instead of sine x. But that is how I solved that problem. Now, any questions about that? I'm going to do some more examples from scratch instead of sort of giving you the sneak preview. But can you see, at least based on this methodology that I have, why that worked? Is everyone happy with that? All right? So let's look at some more examples. Okay, let's consider this. So consider dy dx equals e to the x times y plus e to the 2x. And I'm going to make it into an initial value problem as well. I'm going to specify that y of 0 is equal to the quantity 2 times e minus 1. That's just a constant. Okay, so the differential equation by itself, well, that solution would have a constant in it somewhere, a c. But this is going to allow us to eliminate the c. Whenever you have an initial value problem, ignore this condition until the end. So you have to solve the differential equation first, and then worry about this at the end. So look at this differential equation. Maybe it's separable. Maybe it's actually separable. But if you think about it, that would require getting all the x stuff on one side and all the y stuff on the other side. I don't see how to do that in this case. On the other hand, it's not quite in the form we want. We need dy dx plus something times y. So we'll do this. We'll just bring this over to the other side as plus minus e to the x times y. And that equals e to the 2x. So now that's in the standard form where you have all the dy dx plus x stuff times y, and the x stuff by itself is on the other side. All right, so I now recognize this as first-order linear. I seize the factor outside of the y, and I form my integrating factor over here. All I do is I take that thing, which is negative e to the x, integrate it, and whack this e down. So I'm actually taking e to the power of the integral of minus e to the x. Well, the integral of minus e to the x is just minus e to the x, plus a constant. We don't need the constant. So the integrating factor is e to the minus e to the x. All right, so I've computed that. And now the next step is to multiply through by that integrating factor, e to the minus e to the x. If I do this, the left-hand side becomes e to the minus e to the x dy dx minus e to the minus e to the x times e to the x times y. And don't forget to multiply the right-hand side by the integrating factor as well. E to the minus e to the x times e to the 2x. It looks much worse than the thing we started with, even though we just multiplied through by the same function, e to the minus e to the x, all the way through. But a miracle occurs, and without even thinking, I know I can write the left-hand side as d dx of e to the minus e to the x y. And then the right-hand side is e to the minus e to the x, e to the 2x. A bit of a mess. All right, that is worthy of notice. This is just always what happens. If you get the integrating factor right, you should always be able to factor this. But conversely, I suggest that you take the time to try to just double-check that this actually, if you differentiate this, you get back to the original. Let's just do it in our heads. I have to differentiate this product. One term is just e to the minus e to the x times dy dx. And there it is. The other term is just y times the derivative of this. What is the derivative of e to the minus e to the x? Well, it's e to the minus e to the x times the derivative of this inside part, which is minus e to the x. So if you reverse this as a reality check, you do indeed get the line above. It's kind of surprising, but it works. Again, if you don't see it immediately, it's worthwhile actually just on a little aside writing down that and making sure that you get the left-hand side. Just don't trust the method. You might have got the integrating factor wrong for one, and that will reveal it as well. So stare at that for a few seconds. If anyone has any questions about it, we haven't finished the problem, but you know what to do. Just call it out. My ears are open. All right. Well, we've still got to finish the problem. So let's just, for my sake, at least rewrite that bottom line here. D dx of e to the minus e to the x of times y equals e to the minus e to the x times e to the 2x. Okay, so the next thing to do is integrate both sides dx. And that will kill the d dx here and leave me with e to the minus e to the xy equals, and then on the right-hand side we have to integrate. So you get that dx. All right, so we have an integral to do. Every differential equation has an integral to do, essentially, whether or not you do it. Later on we'll be doing first constant coefficient first and second order differential equations, and there's actually a method that involves no integration, but that's because once upon a time someone did it and they told you and me the method, and then you don't have to worry about it. So in this case, though, we do have to worry about it. How are we going to integrate this? Any suggestions? What method? We've got many. We could do it by parts, but I'd like to do something first before I do parts. Yeah, substitution. So let's set t equals e to the x. I could do e to the 2x, but e to the x is appearing in the nastiest little place up here. And besides, e to the 2x is just then t squared. So in any case, if I do that, I get dt is e to the x. Maybe the way to do this actually is first to write this as e to the minus e to the x, e to the x, e to the x dx. The reason I want to do that is I was inspired by the fact that dt is e to the x dx. So it's nice to kind of bust this up into two pieces here. All right, so what have we got? This is e to the minus t. This is a t. And these two together are a dt. And now we're going to integrate by parts. So to integrate by parts, and this is why, by the way, I like to use t instead of u for my variable for substitution, because now I'm free to use my favorite variables u and v to integrate by parts. So let us say, the t be equal to u, and the e to the minus t dt be dv. So u is t, and dv is e to the minus t dt. So du is just dt. V is negative e to the minus t. Don't need a constant when you do that integral. And so this becomes uv, so that's minus t e to the minus t, minus the integral of u dv, v du rather, which is negative e to the minus t dt. And if you work this out, you get minus t e to the minus t. There's a plus there, but when you integrate e to the minus t, it gives you another minus. So I think you get this expression here, unless I've made a mistake. Now, replace t by e to the x again, and you get minus e to the x, e to the minus e to the x, minus e to the minus e to the x. Be careful, these are minus e to the x's, not e to the minus x's. There's actually no minus x anywhere. All right, so all this was equal to, just bringing it down from there, e to the minus e to the xy. So we will divide, or actually multiply, by e to the x. That will knock out that term. And you'll get y is minus e to the x, that cancels, minus 1, that cancels mostly, plus c e to the x. And I am going to check that answer with what I prepared earlier, and hopefully I haven't made a mistake. Yeah, that looks right. All right. So most of the work was actually in the integral, where we had to substitute and integrate by parts. I will concede we could have integrated by parts immediately, but it wouldn't have been easy to see that you had to bust up that e to the 2x into two pieces. Any questions so far? We still haven't finished the problem, but we've solved the differential equation. So, any qualms, quibbles? All right. Well, we also know that y of 0 is equal to, what was it? I wrote it up here, 2e minus 1. So this means set x equals 0 and set y equal 2e minus 1 in the above equation, and we will get 2e minus 1, that's y, equals minus e to the 0 minus 1 plus c e to the 0. Okay, so the right-hand side is negative 2 plus c e to the 1 is just e. So we need 2e minus 1 is equal to negative 2 plus ce. Well, you add 2 to both sides and divide by e, and you find that c is equal to 2. And so that piece of information allows you to rewrite the solution with the ambiguity gone. Y is minus e to the x minus 1 plus c is 2. So it's 2e to the x. And we know exactly what the solution is. All right, so that's the initial value problem part inserted in there. Any questions about that example? All right. Okay, so what is next? Is next another example? Okay, maybe next is one more example. Here's an example. Tan x dy dx equals e to the sine x minus y. And I am not going to do an initial value problem with this one. Here it is. Okay, so it's linear. I'm going to put the y on both sides. So I get tan x dy dx. I'm going to put the y on the left-hand side, rather. So you get this. Actually, the real specification says that we need to make dy dx by itself. So I have to divide by tan x. Actually, the better way to do that is to multiply by cotan. All right, that's now in standard form. dy dx plus cotangent x times y. So to find my integrating factor, int fac equals e to the integral, and I pull out the coefficient of y, which is cotangent x. And the integral of cotangent is negative cosecant squared. No constant needed. So I'm going to multiply this by e to the negative cosecant squared x all the way through. Wait, there is a mistake. Okay, what did I do wrong? I didn't integrate cotangent very well, did I? Okay, thank you for stopping me before I multiplied the whole equation through. What is the integral of cotangent? Let's just do it. Cotangent x is actually cosine x over sine x. And the integral, the derivative of sine is cosine, so this is actually the log of the absolute value of sine of x. All right, so this should have been e to the log absolute value of sine x, and no constant needed. Now, it's a bit of a pain that there is an absolute value there, so I'm kind of going to be a little bit bad and get rid of it. Get rid of the absolute value. I mean, sine x could conceivably be negative, and if we were really being very precise about this, we'd have to worry about it. But for the purposes, if I can find some solution that makes any sense, so ignore, pull a rabbit out of the hat, and we'll just try use e to the log sine x. Actually, e to the log of something is just the quantity itself, so the integrating factor is sine x. That's a lot better than that stupid thing I was going to write. So multiply through by sine x. You get sine x times dy dx. Well, cotangent is cosine over sine, so actually the sines cancel out, and you get cosine x times y equals cosine x times e to the sine x. And this isn't so bad. Again, the left-hand side always factors into just the integrating factor times y. Okay, let's do the reality check here. Differentiate, you get sine x dy dx, there it is, plus y times the derivative of sine x, which is just cosine x. So we got it right. If I had tried the other thing and we'd done the reality check, it would not have worked. This only works with the precise integrating factor, or a constant multiple thereof. So you don't need the constant, so there it is. Integrate both sides dx. You get y sine x is the integral of cosine x e to the sine x. And that's pretty easy. You just substitute for sine x. The derivative is cosine x. So this is just going to be e to the sine x plus c. And now divide by sine x. To get the solution, y is cosecant x e to the sine x plus constant cosecant x. Now, you might need to take a little more care and possibly have the absolute value of sine x, but actually, that's just plus or minus sine x. And with a minus there, it's not going to make a difference. If you multiply through by minus sine x, everything will still have a minus in front, and you'll get the same answer. So my little sort of dodgy argument there is actually fine. Okay, so I guess the only sort of further thing to talk about is why this works. I might as well just explain it to you. You know, you've got this differential equation here, dy dx plus p of x times y equals something, and it doesn't matter what that something is, the first thing we do is multiply by the integrating factor, e to the p of x dx. Right? So let's do it. You get e to the integral of p of x dx times dy dx, that's one term, plus e to the integral of p of x dx times p of x times y equals different stuff, which we had to deal with later. The main thing is that this left-hand side is supposed to factor into d dx of the integrating factor, e to the, it's not the integral, but it is e to the integral of p of x dx times y. So let's just check that that works in general. Hell, it's worked in all of our examples. Why shouldn't it work in general? Well, you never know until you try. One term will be e to the integral of p of x dx times y, times dy dx, rather. And there it is. The other term is y times the derivative of this. So everything comes down to, is this quantity the derivative of this quantity? Well, when you differentiate this, e to the anything has derivative e to the same thing, and then you just have to multiply by the derivative of this thing, but the derivative of the integral is just p. So don't worry if you didn't follow all of that. It's worth staring at for a few seconds, but you don't need that to do the method. You don't need to know how it works. It's kind of helpful to understand how it works. At least then you'll have confidence that it works. But of course, I still think you should always check the actual form that you have just to make sure that you got the integrating factor right. So I just do a mental check as I did in those examples. So that's basically the whole topic of first-order linear differential equations. So I'm proposing to move on to the third of the three types of differential equations, which is the most involved and will take most of the rest of this time. As I'm clearing some space for myself, if anyone has any other questions about the first-order linear case, please begin. All right. No questions? No. So in that case, the third of three types that we're considering. There are many, many different types of differential equations. We've only looked at three of the most straightforward types, or rather we will have looked at three. This is the third, as I said, and it's called constant coefficient. Const coefficient. All right, so the general sort of idea is that we're going to take something that looks like a polynomial, but instead of the powers, x to the n, I'm going to take the derivative, the nth derivative. And then I'll take another constant, and I'll take the n minus 1th derivative. And I'm going to work my way down until I get some constant times the second derivative, plus some constant times the first derivative, plus finally a constant times the 0th derivative. And remember, the 0th derivative of y is just y. You take no derivatives, the 0th derivative. All this equals some x stuff. Say f of x. So actually, in this, all these ANs are just numbers. They are constant coefficients. They're not functions of x. There's no stuff in x on the left, just in the derivatives with respect to x. And there's no stuff of y on the right-hand side. All the x stuff by itself is on the right-hand side. All right, so that's the type we're looking at. Luckily for you guys, in this course, we're only looking at first order and second order. So that kind of cuts things down to size. Here's an example of a first order. If I took, say, 3 dy dx minus sine of 5x equals 12x minus 6y. Well, I could rearrange this to put all the x stuff on the left, on the right rather, and all the y stuff on the left, and I get 3 dy dx plus 6y equals 12x plus sine 5x. Now, actually, this case it's actually an example of a first-order linear as well. If you divide by 3 in particular, which you don't need to do, but you might as well, then everything comes down to this. So you can actually solve this using the first-order linear technique, but it's nicer than linear. You don't even have any stuff in x here. It's just a number. It's just a 1 here and a 2 there, so it's really constant coefficient. The methodology will prove, I think, to be nicer than the linear case. So this is first order with coefficients 1 and 2, and then this other stuff in x on the right. Okay, so let's look at a second order case. I'm not going to tell you how to solve it just yet, but we'll come back to it. If not this example, and other examples. So a second order case, this is a first order. Second order example would be something like this. d2y dx squared minus 5 dy dx plus 6y equals 2x squared e to the x. Okay, so it's constant coefficient. The derivatives are all on this side, including y itself, the zeroth derivative, and they just have constants out the front. And then on the right-hand side, there's nothing to do with y. It's all x. So this is the sort that we're considering, and this is actually the first second-order differential equation we've looked at. Everything we've done so far was first order, separable first order and first order linear. Okay, so now we're touching on second-order differential equations, and as you might expect, they are a little more difficult. They also are going to involve two integrals, or two integrations, which may be hidden from our view, as I said, by the method. However, they will involve two constants, two derivatives, two integrations, therefore two constants for second order. All right, so in order to show you how to solve equations of this form, I've got to break it down and consider a simpler case first. I'd like to consider what's called the homogeneous case. And that is the right-hand side equals 0, i.e. no x stuff. There's no x stuff. So let's look at a simple example of first order. So first order, we may have an equation that looks like this. dy dx minus 3y equals 0. I'm not allowing x stuff there. So how do we solve this? Well, we actually just write down the solution. We've seen what the solution is. It's a separable differential equation, but it's such a common thing, we might as well realize that y is a to the 3x will work for any constant a. This is just the population growth one, and we looked at it last week when we did separable differential equations. That's at the end of last week's video, if you haven't seen it. So just a reality check, I mean, dy dx just spits out a 3, and you get 3y. No problem. In general, it is worth knowing that dy dx plus ay equals 0 has solution y is capital A e to the minus ax. Even though you can work it out pretty quickly, it's so common that you're supposed to just know this. And of course, a is a constant that you do not know unless you have an initial condition. So the first order constant coefficient is nothing more than the population dynamic equation. If you do have a coefficient out of here, you just divide by that first, and everything goes into here, sort of like we did in the above example. All right, so the first order case of homogeneous, where the right-hand side is 0, is a piece of cake. It's a piece of cake. You just got to know that formula, and it's not hard to see why it's true. So are there any questions about that before I move on to the second order case?
We ask why we included a, or include
Sorry, what's the question? Well, I did it last time. I mean, the fact is it's a separable equation. Last time I looked at the solution of dy dx equals ky. And here k is 3. And we saw the answer is ae to the kx. Right? So here, the only difference is I called k minus a. All right? So I leave it to you as an exercise based on what I said last week. It's a separable differential equation. Now, the second order, of course, is not separable because we don't even know what it means to be a separable second-order differential equation. So there is a nice little technique that involves, again, pulling a bit of a rabbit out of a hat. I'm not going to have much time to justify it, unfortunately, but there is a comprehensive justification in the book. Here's the idea. Suppose we have, so for second order, homogeneous. Remember, homogeneous means we have 0 on the right. I'll give you an example, and then we'll solve it. So an example might be y double prime minus y prime minus 20y equals 0. This is just a fancy way of writing d2y dx squared minus dy dx minus 20y. So it's a constant coefficient linear differential equation. So second order because there's a second derivative here. Now, here's the basic idea. I take the coefficients out of this. Here there's a 1, here there's a minus 1, and here there's a minus 20. And I form what is called the characteristic quadratic equation. Characteristic quadratic equation. And it's a weird thing to do, but what I do, I don't remember which variable I used for this in my book. I'm going to use a lambda, just to be difficult. Maybe that's what I did. I take the coefficient 1, and I write 1 lambda squared. I take the coefficient minus 1, I write minus 1 lambda, and then I take the coefficient 20, and I wrote minus 20 equals 0. Or just regularly lambda squared minus lambda minus 20 equals 0. So that's not a differential equation. Lambda is just supposed to be a number. Nevertheless, watch this. I factor this, if possible. Well, in this case, it is possible. It factors into lambda minus 5, lambda plus 4 equals 0. And so the solution is lambda equals 5 or minus 4. So what? Well, amazingly, this means that the solution to the dE, to the differential equation, the original one up the top of the board, is y equals some constant a, e to the 5x, plus b, e to the minus 4x. Where did these numbers 5 and minus 4 come from? There they are. So the roots of this characteristic quadratic equation are exactly the multiples of the x in the exponents. Bizarre. It bears checking. We should check whether this works. The best way to check is to realize that the a and the b don't really matter. All you have to do is check e to the 5x. And then any multiple of it will automatically work because it'll just be a factor of the whole thing. The same with the multiple of e to the minus 4x, and the same with adding the two together. If you differentiate this plus this, it's the same as differentiating them one by one. And the same with the second derivative. So everything will just sort of split up. So I don't know, check e to the 5x. We have e to the 5x. Suppose y is this. We'll check that that's the solution. What is y prime? It's 5e to the 5x. And y double prime is 25e to the 5x. So if I plug this into the differential equation, I get y double prime minus y prime minus 20y is equal to 25e to the 5x minus 5e to the 5x minus 20e to the 5x. And sure enough, 25 minus 5 minus 20 is 0. It's like magic. But actually, it's not so much magic, because the second derivative is really the 5 squared comes out. and the first derivative, the 5, comes out, and it's like 5 squared minus 5 minus 20. It's like plugging 5 into that characteristic quadratic equation, which of course gives you 0. So that's why this works, at least in this case. And in general, it's not that much different. So at this point, I'd like to tell you the general method, of which this is a special case. And then I'll give you a couple of other examples. So the general method of this is as follows. And this, I'm afraid, is something you just have to commit to memory. It's a bit annoying, but it's too finicky to develop on the fly. So you're just going to have to remember all this. So you have the equation ay double prime plus by prime plus cy equals 0. And what you do is you write down the characteristic quadratic equation, which is a lambda squared plus b lambda plus c equals 0. And you try to solve it. Now, in this previous example, I was able to factor it and find the two solutions. But there are actually 3 cases, depending on the sign of the discriminant. And remember, the discriminant is, as always, b squared minus 4ac. So the first case, case 1, is where the discriminant is positive. Then there are 2 real roots. Which I'm going to call alpha and beta. And in this previous example up there, the alpha was 5 and beta was minus 4. It doesn't matter if you write them in the opposite order. So then the solution is y is some constant e to the alpha x plus b times another constant e to the, or b is the other constant, e to the beta x. So you fill these in. So in this previous example, I followed this method exactly. I found the roots were 5 and minus 4, and I knew that the solution a e to the 5x plus b e to the minus 4x would work. So this actually works in general, provided that you have 2 real roots. Now sometimes you only have 1 real root. If, for example, if precisely the discriminant is 0, that means that this has a double root. There's a double root. 1 real double root alpha. Now, you'd like to do the same thing. You'd like the solution to be y is a e to the alpha x plus b e to the alpha x. But that's kind of silly because a and b are constants, and you could just add them up to a plus b to get another constant. So that there wouldn't be 2 constants. But because there's 2 derivatives, there sort of have to be 2 constants. So I need an x in there, and believe it or not, that works. Again, the explanation is in my book, but I don't have time to do it. Or you can try doing it for yourself. It's kind of nice. It's kind of nice. So you get almost the same thing, but the second thing, because these are the same, you need to put in an extra x. The third possibility is that the discriminant is negative, which means that when you pull out the quadratic formula, minus b plus or minus the square root of b squared minus 4ac over 2a, the square root is going to be of a negative number. Well, how do we deal with that? Complex numbers. That's why we spent some time on that. That's one of the reasons why, anyway. So, 2 complex roots. And what you have to do is realize that they can be written in the form y is alpha plus or minus I times beta. We'll see an example of that soon. So the roots must be alpha plus or minus I beta, where I is, as it was last week and the week before, the square root of minus 1. In this case, the solution is y is e to the alpha x. It should really be e to the I beta, or something like that. But remember, Euler's formula says that e to the I beta has something to do with cosines and sines. And so it may not be such a surprise to learn that we now have A cosine beta x plus B sine beta x. And that, again, I cannot, this is a B, not a beta. I cannot really justify this for you on the fly. It's something that you have to just work out and see and make sure that it works, or read it in the book. Now, in all the cases of here, A and B are constants, which are not known unless you have an initial value problem. In all three cases. Okay, I'm afraid you simply have to memorize what's on that blackboard. It would be nice if you sort of had some idea of why it's true. Many, many students have managed to get by having no clue and just turning the crank. But you're in college and you're supposed to have inquiring minds, so it might be worth taking the time to inquire. And I tell you, anyone who has actually worked it out and verified that these all work somehow never manages to get these things wrong, or very rarely. You know, it sort of really cements that understanding. So I think it's actually a good way to study for these. And these problems come up on the Math 104 final almost every time. Right, so I've got to give you two more examples. I've given you an example of the first type. Let's look at an example of the second type. Y double prime plus 6y prime plus 9 equals 0. So let's check that out. It's a homogeneous equation because of the 0 on the right. Let's form the quadratic equation lambda squared plus 6 lambda plus 9 equals 0. And this factors into lambda minus lambda plus 3 all squared equals 0. So lambda equals minus 3 is a double root. So according to the method, the solution to this, you can just write straight down. It's y is a e to the minus 3x plus b x e to the minus 3x. And you know, you should probably write a and b are constants. All right, so that one's fairly straightforward. How about this one? Y double prime minus 2y prime plus 5y equals 0. Again, straightforward, second order, constant coefficient. So the characteristic quadratic is lambda squared minus 2 lambda plus 5 equals 0. Doesn't look like I can factor that easily. So let's try the quadratic equation. Lambda is minus b, which is 2, plus or minus the square root b squared minus 4ac. Well, what is that? That is 4 minus 20 over 2, which is 2 plus or minus the square root of minus 16 over 2. What's the square root of minus 16? Yes, a question. Well, are you answering the question or a different question?
I had a question about the top. Y double prime plus 6y, 5 plus 9, y are 9.
Oh, yes, thank you. Let's go back to here for a second. I miswrote down the question. Thank you for pointing that out. There is a y there. Without the y, you're in worse shape. You'd have to do something else. It is actually then a first-order linear equation in dy dx, but that's beyond the scope of this course. So, okay, thank you for pointing that out. Any other questions or mistakes that I've made before I go on? Okay, so the square root of minus 16 is 4i, or minus 4i. We've already got those covered. So this is 2 plus or minus 4i over 2, which is 1 plus or minus 2i. So according to the spec, this is like alpha plus or minus beta I, and we can write down the solution as y equals e to the alpha x, alpha is just 1, times a cosine of beta x, well beta is 2, plus b sine of 2x. So the 1 from here comes from this 1 down there, and the 2 in both places come from this 2. Okay, So it's a bit of a turn the crank and pull and all that and just run it through. And of course, the more of them you do, the better. But as I said, if you take the trouble to understand why it's true, then you probably don't even have to do so many of them. But you make sure you understand all three types, because the solutions look a little different. All right? Any questions about that? Okay. So we know how to solve first and second order homogeneous equations. Oh, by the way, the explanations, I should give a reference for it. Explanations are in 30.4.3 of my book, chapter 30. All right, so moving on to 30.4.4, we're going to look at the non-homogeneous case. And this means that it's not just a 0 on the right-hand side, and we have to do some serious work. All right. So here's an example. Suppose I take the example from the previous board, y double prime minus y prime minus 20y equals 0. Well, I'm going to change the 0 to e to the x. What's the solution of this? Well, let's guess. Let's try a guess. Let's guess y equals e to the x. Ah, there it is on the right-hand side. What the hey? I mean, that's pretty simple. Y prime is e to the x in that case, and y double prime is e to the x too. So we'll plug it in, and we get e to the x minus e to the x minus 20e to the x. If that's a solution, this would equal the right-hand side, which is e to the x. Okay, so I've just plugged in e to the x, y equals e to the x into this equation here. The left-hand side is actually minus 20e to the x, and that's certainly not equal to e to the x, but it's pretty close. It's pretty close. It's just, well, I mean, it's got an e to the x on both sides, so all I have to do is divide by minus 20. So instead, y equals minus 1/20th e to the x. Let's try that. Now dy dx, or y prime, is the same thing, and y double prime is the same thing. And when I substitute it in, I'll get a minus 1/20th outside of everything. So minus 1/20th e to the x, that's y double prime, minus 1/20th e to the x, that's y prime, minus 20 outside of minus 1/20th e to the x equals e to the x. We don't know. Let's see. I get minus a 20th plus a 20th, so that cancels. And minus 20 times, look, I got e to the x. Yes. So I found a solution just by brute force in this case, by guessing it, more or less, to the differential equation. Now, here's the real question. I'm going to say it to you, and then I'll take a show of hands. So who thinks that that is the only solution, or who thinks that is not the only solution? So that's going to be the question. And I'm going to take a informal straw poll of everyone in the room, since I cannot tell what anyone watching online thinks. So who thinks that minus 1/20th e to the x is the only solution? Okay, who thinks it's not the only solution? That's pretty good. That's pretty good. You all think it's not the only solution, and you are all right. The reason that it is not the only solution, or that it cannot be, is because there's no constants. There has to be two constants, since we don't have an initial value problem. Right? So where are they going to come from? Well, here's the real nub of the situation. We saw that the solutions of y double prime minus y prime minus 20y equals 0, we saw that a e to the 5x plus b e to the minus 4x will work. Now let's take a look at this. Here's the new equation. It has an e to the x on the right-hand side. And we saw that y equals minus 1/20th e to the x will work. So what happens if I take any of the solutions? You pick a and b, any two numbers. That will solve this. What happens if I add that onto here? Well, again, it's sort of worth trying yourself. But you'll find when you do the derivatives that everything breaks up into a derivative of this, a derivative of this, and a derivative of this. So you can kind of separate everything and consider separately this plugged in, which gives you e to the x, this plugged in, which gives you 0, and this plugged in, which also gives you 0. So when you plug in this, what I'm claiming, and again, try it for yourself, I'm claiming that y double prime minus y prime minus 20y will give you out of this e to the x, out of this 0, and out of this 0. And here comes some sneezes. Just one? No, there's a lot of chalk. Thank you. The thank you is not for any sort of applause, but rather the people who said it. All right. Okay, so, no, this is not e to the 0, this is 0. That was a sneeze-induced mistake, so it doesn't count. So the end result here is that I have e to the x. And these solutions of the homogeneous version of the equation did not change the answer. Okay, so this suggests the general sort of paradigm. Regardless of whether it's first order or second order, I have a constant coefficient equation, say second order for sake of argument. Okay, so the general idea is that first, consider a y double prime plus b y prime plus cy equals 0. That's the homogeneous version. The homogeneous version of the equation. And you solve this using the method that we just did. And you call the solution YH. Capital H I use for homogeneous. Okay, that's not the solution of this. Then you have to guess a solution. And I'll talk more about that very, very soon. But I'm going to call this YP. And somehow I have to do a sort of futzing around to get the constants right, just like I did in the previous example, to get that minus 1/20th. I kind of had to guess and then plug it in and then adjust. So this is going to be, it's going to involve plug in to pin it down. And again, I'm going to talk about this very soon. And find exactly. No constants. So there's two constants here, if it's second order, or one constant if you started off with only first derivatives. But when you did this part, there's no constants. Unknown. There's just everything is known exactly. And so I call this solution that we guessed and pinned down. P is not for pinned down, P is for particular. It's a sort of special solution that is particular to the X stuff that happens to be there. And then finally, the actual solution, Y, is the sum of the homogeneous and the particular. So that's exactly what we had up there, although I wrote the particular solution first. I wrote YP plus YH. Okay, so that's the general gist of the way to solve these non-homogeneous things. First, do the homogeneous, call it YH. It'll have two constants, maybe one if it's the first derivative, if it's the first order. Then go back to the original, restore the X stuff, and plug in a guess. And then futz around with it until it's right, and more on that in a second, and you get your YP with no constants. You know it exactly. And then the solution is the sum of these two. Because when you plug it in, that gives you 0, and that gives you the actual X stuff on the right. All right? So, what is missing is that I have to tell you how to guess a solution, and also how to pin it down by plugging it in. And this is not the most general method of doing it. There is a method called variation of parameters. I didn't discuss it in my book, and it's not in this course, although some of you might have learnt it or might be learning it in your regular class. But as far as I'm concerned, or as far as I believe, it's not examinable in this course. I may be wrong about that, but I haven't checked it this semester, but certainly in previous semesters this was true. So maybe just ask if you're in the room or watching for Math 104, just check whether variation of parameters is examinable. And if you didn't do it in class, it's not examinable. You don't even need to check. All right, so here's the idea. We've got one of these things, and you've got this x stuff on the right, and I'm telling you have to guess a solution. And the way you do it is very similar to what you do with partial fractions. Remember there we looked at the denominator, and we came up with a form. And we don't know what the constants are, but we know what the general form is. Well, it's the same sort of trick here. There's a form. It involves some constants, but you can actually find these constants by plugging them in. So there is a table on page 659 of my book, but I am going to rewrite it for your convenience and describe what's going on as I do it. So the table actually, you know what? It's going to take up 2 boards because this is a big table. So I'll eschew that space and use all this. Okay, so what I'm trying to say is the form of the solution depends entirely on what you see on the right-hand side, that x stuff of the right-hand side of the original equation. And so I'm going to say if the right-hand side is A, then the form is, and that's the headings of this table. All right, so what are some of our favorite objects? Well, one is a polynomial of degree n. Okay, so if you see a polynomial of degree n, then the form should be a general polynomial of degree n. For example, if the right-hand side is, and let's call it f of x for definiteness, if f of x equals, say, 7, so if the right-hand side, for example, is 7 instead of 0, 0 would be homogeneous, and then you don't need to muck around with these particular solutions at all. But if the right-hand side of your original differential equation was just the number 7, then the form is a general polynomial of degree 0. So the form would just be yp is just some constant a. And this is not the same a that appeared in the differential equation. This is an a that you write down. So I'm sort of reusing letters, but you will forgive me, I hope. Suppose that the right-hand side of the original equation was 3x minus 2, for example. Well, that's now a linear function. So you put ax plus b here, and you have to find what little a and little b are. Another example, if f of x is, say, minus x cubed, then the right-hand side would be ax cubed plus bx squared plus cx plus d, and you'd have to find all 4 of those constants. So polynomials, pick the degree of the thing, and replace, just write down a general degree. All right. Suppose it's a multiple instead of an exponential, e to the kx, where k is some particular number. So the right-hand side of the original differential equation is an exponential, or a multiple of an exponential. Well, then, the form should be yp is equal to some constant. I guess I've called it capital C. That was pretty dumb. Let's call it a, e to the kx. So, for example, if the right-hand side is 10e to the minus 4x, so that appears on the right-hand side of your original differential equation. Well, then you immediately set yp is a e to the minus 4x. Forget the 10. That's not necessarily right. Or if f of x equals just e to the x, then the particular solution would be just a constant e to the x. And that's actually the example that we looked at. Remember, we got a minus a 20th. There, if we had just substituted a e to the x instead of e to the x first, we would have seen that a would have to equal minus a 20th to match the sides up. So we've already seen an example of this particular row of the table. All right, there's a few other types. What if you end up with a multiple of cosine kx plus a multiple of sine of kx? And maybe it's just cosine by itself, or maybe it's sine, or maybe it's some combination, but with the same number here. Well then, the guess that you make is also a general multiple a cosine kx plus b sine kx. For example, if f of x happens to be, that this is the right-hand side of your original differential equation, 2 sine 3x minus 5 cosine 3x, then the particular solution that you guess is a cosine 3x plus b sine 3x. All right, what if f of x just happens to be equal to cosine x? Well, do not make the mistake of letting yp be a cosine x. You also need plus b sine x. Wherever you have a cosine, you need a matching sign to make this technique work, and vice versa. If f of x happened to be equal to 2 sine 11x, then yp would be a cosine 11x plus b sine 11x. Okay, so those three, polynomials, exponentials, and just sines and cosines, are the basic types that are amenable to this method. Also amenable to this method is combining the types by summing or producting of one of the above. So sum or product, or a difference, whatever, sum's the same as a difference, of above. And I'm going to write that then you also get the sum or product, as appropriate, of the forms. And I'm going to add something a little cryptic, which will make sense in a few seconds. If a product, omit a constant. Omit a constant. Okay, don't worry about what that means. It will become clear when we look at a bunch of examples in this category. So, if the right-hand side of your original differential equation happens to be 2x squared plus e to the minus 6x, well then, you let yp be, well the 2x squared needs to be ax squared plus bx plus c, and the e to the minus 6x, I'm a little bit suspicious. It should be a constant. I've run out of letters. Actually, maybe I'll call it c. What the hey? C e to the minus 6x. Right? Why not d? Because I can't write d without thinking of it as a derivative. You should. I didn't use a big C. I used a little c. Okay, call it whatever you like. Call it q. Just yes, they're not equal. They're not equal. Call it q, but don't call it d, and for heaven's sake, don't call it e. E to the minus 6x. No. All right. So you see though that I've added the forms for the two. No problem. Now, what about a product of these two? 2x squared e to the minus 6x. Well, here you might think that it should be the product of the two forms, and you are right, except you don't need the q anymore, or whatever you wanted to call it. You don't need the q. If we called it q, you omit the q. Omit. The reason being that if q is a constant and you multiply it by a, b, and c, you can rename a to be aq. So aq is now a, bq is now b, cq is now c, and the q has been absorbed. So when you're multiplying two of these forms, there's always one constant to spare that you should omit. So that one goes with that. Here's some other examples. F of x equals 7e to the 2x times sine 3x. Well, in this example, yp, 7e to the 2x should be giving me e to the 2x times a constant, but I'm going to omit that constant, and I will instead put it under the a sine, well, cosine 3x plus b sine 3x. Again, I don't need the constant out the front because I've got the a and the b to absorb that. All right, what else? How about this? F of x is equal to cosine 2x plus 6 sine x. Oh, well, I've got a cosine and a sine, right? No, this one needs a cosine and a sine. This one needs a cosine and a sine. So it will be yp equals a cosine 2x plus b sine 2x plus, let's say, q cosine x plus r sine x. I could have used capital A and B there, or capital A, B, C, D all the way along. I think that's what I did in the book, actually. No, I used C, D, E, and F, but capital E, so it's okay. And finally, another example of this, and the last example in the table, would be 4x cosine 3x. Well, here, 4x is linear, so it should be ax plus b. I'm just going to write it as x plus b. I don't need a constant there. And then for cosine 3x, let's say q cosine 3x plus r sine 3x. I had to omit one of the constants, and I chose to do it the a outside of the x there. Otherwise, you just have a spare constant that you can't possibly find that would come out the front. So there's the complete table. I do have one thing to say, which is not going to make any sense whatsoever, but we'll come back to it. If yp conflicts with yh, multiply by x or x squared as appropriate. And as I say, I can't explain that right now, but I will shortly. I just want to put it in that table for completeness so we have it all in one spot. All right. Time is running away. I doubt that I'll have time to do the very last little bit on modeling with differential equations, but I will certainly finish this topic. All right, well, I got to do some examples of all this, and then I've got to come back and tell you what that last little cryptic statement means. So, let's see how many examples I can actually get through. All right. Here's an example. Y double prime minus 4y prime plus 4y equals 25 e to the 3x sine 2x. All right. Okay, well, how do we do it? First, the homogeneous version. Y double prime minus 4y prime plus 4y equals 0 has characteristic quadratic lambda squared minus 4 lambda plus 4 equals 0. Factors into lambda minus 2 all squared. So lambda equals 2. So I immediately have YH. This is the only solution, by the way, double root. So I have YH is equal to A e to the 2x plus B x e to the 2x. All right. So that's the homogeneous part. Now, let's deal with the particular part. We need to guess a solution. According to this table that I've just written up, we have a product of two things. The e to the 3x bit, I'm going to use e to the 3x. I should have a constant out there, but I don't need it because it's a product. And I'm going to use here capital C cosine 2x plus capital D sine 2x. I don't want to use A and B because they're already used over there. Right, so that's my guess. Now, in order to work this out, I unfortunately have to do the derivatives. Now, let's write this out as C e to the 3x cosine 2x plus D e to the 3x sine 2x. All right, so that's what yp is. So how about yp prime? Well, you've got to use the product rule twice. So you're going to get C, you're going to get V du dx. So 3C e to the 3x cosine 2x. And then you're going to get 2 minus sine. So it's minus 2C e to the 3x sine 2x. And then on this term, we'll get, again, 3D e to the 3x sine 2x. And there'll be one more term from the derivative of the sine. That's going to be 2 cosine. So it's 2D e to the 3x cosine 2x. And it's a bit of a mess, but you notice you can group some terms together. If you do group the sines and cosines together, you find that the derivative is 3c plus 2d times e to the 3x cosine 2x plus 3d minus 2c e to the 3x sine 2x. So there's the first derivative. Unfortunately, you have to repeat the dose. Yuck. But if you're really, really clever, you can avoid it. You see, notice that the first derivative looks like the actual function. So if you mentally replace this by c, or c1, and this over here by d1, and then apply the same process, but you see the coefficient of this thing would be 3c1, so it's 3c plus 2d, plus 2d1, 3d minus 2c. So that's the coefficient there. And we do the same thing for the other term, 3d, but d gets replaced by 3d minus 2c, minus 2c, but c gets replaced by 3c plus 2d. If you really are suspicious of this, then just differentiate it. Don't get fancy, just do it. Anyway, we can simplify it a little bit. I agree this is a horrible mess, but that's life. 3c, so you're going to get 5c plus 12d e to the 3x cosine 2x plus, gee, I hope I didn't make a mistake doing this fancy schmancy method, minus 12c, and how many d's do I have? 9 minus 4 plus 5d e to the 3x sine 2x. Okay, so if everything has gone correctly, then I have finally written down the first derivative, the second derivative, as well as the original function. Now, time to plug in all the pieces. I need to plug it into the original differential equation. Y double prime minus 4y plus minus 4y prime plus 4y. And that equals some unholy mess. Well, YAP is e to the 3x. I'm just copying this from above. What, that little mark? Where? There's no prime there. There's this little square there. You asked me why I have that. Okay, I did it by mistake. All right, thank you. Okay, I fess up to it. Okay, so yp is ce to the 3x cosine 2x. You could get a sore neck from this. Minus de to the 3x sine 2x. Okay, minus 4 times the derivative. 3c plus 2d e to the 3x cosine 2x plus 3d minus 2c e to the 3x sine 2x. What the hell? I've got this wrong. The top line is supposed to be the second derivative. You try standing up here writing this junk. Look at it. It's hideous. Hard enough to do on a piece of paper. There's the second derivative, just copied directly from the line above. That's y double prime minus 4y prime plus 4y itself. Now here's where I pull out the y from above. C e to the 3x cosine 2x plus d e to the 3x sine 2x. Yuck. Okay. Anyway, now I can group this. I have in the cosine column 5c minus 12c plus 12c. No, plus 4c. So 5 minus 12 plus 4 is minus 3. Minus 3c e to the 3x cosine. Well, I should do the d's as well, huh? How many d's have I got? 12d minus 8 is 4, and that's it. So it's minus 3c plus 4d e to the 3x cosine 2x. And in terms of the sine column, c's minus 12. Don't forget the minus 4 all the way out here. And so it's minus 12 plus 8 is minus 4. And so I have a minus 4c. In terms of the d's, I have got a, what have I got? I've got a 5d minus a 12d, with the minus 4 out there, is negative 7, plus a 4d. All right. Did I get that right? Who knows? We'll find out soon. What, do you have to know how to do this question? Cha. I don't see why not. We're nearly done. We're nearly done. Come on. This had to be equal to 25 e to the 3x sine 2x. Look, it's just computation. I mean, it's messy, I admit. But how are you going to match these things up? The only way you can do it is if the cosine bit minus 3c plus 4d is 0, and the sine bit is equal to 25. So that's how these things have to match. So for this to work, we need minus 3c plus 4d equals 0. And we need minus 4c plus 3d equals 0. And you can solve these things simultaneously. Equals 25. Man. Right, so let's just review this. I don't know how you're going to get this on the camera. But this bit has to be 0, whereas this bit has to be the 25, so that this thing matches. And the solution turns out to be c equals minus 4 and d equals 3. If you plug that in, it's just simultaneous equations, you're going to get... No. What is the solution? It's just 4 and 3. Would that be nice? It would be nice, except that somehow there shouldn't be a minus here. Okay, where is there no minus? Why is there a minus there? Why is there not a minus there? I don't know. I don't know. Where did it go? Where did it go? This is very unfortunate. Oh, wait. No. They're both supposed to be minus. Okay, so now minus 3c plus 4d equals 0. So it's minus 4. I just got the d wrong. I got the d wrong. Why did I get the d wrong? Because there's a 5 minus 12 plus 4. Yes, it's negative 3d. Aha. I said minus 3, but I think I wrote down plus. So there we go. So now the solution is minus 4 and minus 3. So we finally found the particular solution. Yp is equal to minus 4 e to the 3x cosine 2x, minus 3 e to the 3x sine 2x. Okay, I admit this is pretty tedious and difficult, but it is fair game, unfortunately. But on the other hand, we will let you have plenty of time to solve it if we do ask something that tricky. Maybe I should have done a simpler example first. Oh well. There are actually quite a lot of examples in the book, and you should definitely read through them. I obviously don't have time to go through all of them now because the computations turn out to be pretty nasty. But you should do them yourself and see if you can duplicate the solutions in the book. I did actually check them in a mathematical program to make sure that they were right. It didn't stop me from getting the separable thing wrong, though, so no guarantees. All right. Let's finish the problem. All we have to do is write down the answer. Y equals YH plus YP. And it seems long ago that we wrote down YH on the top board over there as A e to the 2x plus BX e to the 2x. And finally, I am going to put in the particular solution, which is actually minus 4 e to the 3x cosine 2x minus 3 e to the 3x sine 2x. And there it is. That's the answer. Woo! All right. Yeah, not so easy, huh? But practice makes perfect. All right. Here is a slightly less exotic one. First order case. Y prime plus 2y is equal to 4x plus a third sine 5x. Now, you could treat this as a first order linear, as I said, because all the x stuff is just there. It is a linear first order equation. But this is much more amenable to the sort of techniques that we've just done because it is constant coefficient. So the homogeneous version is y prime plus 2y equals 0. The solution to this is y is constant a e to the minus 2x. And that's the homogeneous solution, yh. Now let's come over and guess a particular solution. This is a lot easier. It's just a linear function, ax plus b, plus, say, c cosine 5x, plus d sine 5x. And because it's only a first-order differential equation, I only need one derivative. Hallelujah. Y prime is a plus, or actually minus 5c sine 5x, plus 5d cosine 5x. So we're going to plug yp prime and yp into this equation. And you get yp prime plus 2yp equals, well now, let's put in that yp prime expression. A minus 5c sine 5x plus 5d cosine 5x. And plus twice the yp, which is ax plus b plus c cosine 5x plus d sine 5x. All right, let's group similar terms. The x term is just 2ax. The constant term is a plus 2b from over there. The sine term, well, let's do the cosine term first. It's 5d plus 2c from there. And the sine term is, well, we have a 2d from over there, minus 5c from over here. And this is supposed to be equal to the right-hand side of the original equation, 4x plus 1/3 sine 5x. Well, how are we going to make this so? The 4 here has to match the 2a over there. So we'll have 2a equals 4. Yes, question.
You have 5d plus 2c times cosine 5x.
Yep.
Plus d sine 5x, or you could also someplace else.
Well, I did the 5d cosine 5x, and I grabbed the 2c cosine 5x from over there. And then the sine 5x, I had a minus 5c from there and a 2d from there. So that's, I just grouped it. Did I make a mistake? Another.
Yeah, 2d minus 5c sine 5x. Then
Oh, yeah, that's definitely a mistake. Thank you. Yeah, that's a 5 here. Right. Okay, so if I want this to match, then I need the 2a to be equal to 4. I need that constant term, a plus 2b, to be equal to 0. I need the cosine term, 5d plus 2c, to be equal to 0. And I need the sine term, 2d minus 5c, to be equal to 1/3. See, I've just matched the coefficients, just like in partial fractions, of the different items there, and some of which don't appear, so they're 0. The a plus 2b and the 5d plus 2c. So if you work this out, a equals 2, b is equal to minus 1, and unfortunately these don't work out so nicely. I believe, if I'm not mistaken, that c works out to be minus 5/87, and d is equal to 2/87. So the particular solution, yp, is equal to ax plus b, so it's 2x minus 1, minus 5/87 cosine 5x, plus 2/87 sine 5x. And of course, the actual solution, y is yh plus yp. And the homogeneous solution I found in that little box up there is a e to the minus 2x. And yp is just this, so rewrite. I'm not going to do it to save time. All right, that's an easier example. That's probably about as easy as these sorts of questions get, I'm afraid. But just think about how long partial fractions questions take. They also take a long time, and they can be quite messy. And so this is sort of very similar in principle to a partial fractions, at least by method of solution, if not actual problem having anything to do with each other. All right. Time is flying, but are we having fun? Maybe, maybe not. Okay, I have a few more things that I need to show you. One involves initial value problems. But before we do that, I got to tell you what I meant by that cryptic line about resolving conflicts between yh and yp. So that was that last line of the table. Unfortunately, sometimes the form is still not going to be right. I'll give you an example here. Consider y double prime minus 3y prime plus 2y. This one's not so brutal, but it will be a little tricky because of one particular fact. Okay, so y double prime minus 3y prime plus 2y equals 7e to the 2x. Okay, so the homogeneous version, y double prime minus 3y prime plus 2y equals 0, has characteristic equation lambda squared minus 3 lambda plus 2 equals 0. And it factors into lambda minus 2. There's a plus here. Okay, lambda minus 2, lambda minus 1 equals 0. So lambda is 1 or 2. Two solutions. So the homogeneous solution, yh, is equal to a e to the x plus b e to the 2x. No problem. So what about a particular solution? Well, the particular solution, we've got a constant multiple of e to the 2x, so the particular solution should be c e to the 2x. Right? That's what the table said anyway. Now, what's the problem with this? What do you think you will get when you plug this into there without even doing it? What do we get? Can anyone tell me? Sorry? Why do you get a conflict? What do you actually get? You don't get a conflict, you get an answer. What is the answer? You could be conflicted about it, but what do you think the answer is? Well, what do you think you get when A equals 0 and B happens to be the same as this C? You get the same as YP. And of course, if you plug this in, you get 0. So what I'm trying to say is, if you plug this in, you get 0, because this is contained within YH. This is one of the homogeneous solutions. Regardless of what C is, it is a homogeneous solution with A equals 0 and B equals C. So that's no good. You have to recognize, you don't have to, you could plug it in and you'll get 0. That's what I mean by the conflict. You'll get 0, which doesn't tell you much. In fact, it can't possibly be equal to 7e to the 2x. So in order to get around it, according to the instructions in the table, you have to multiply by x, or possibly x squared. In this case, x will be good enough. So I'm going to multiply by x. Okay, this is because of the conflict. This resolves the conflict. It also means we have to use the product rule, so let's do it. Yp prime is c. So you get e to the 2x times the derivative of x, rather, plus x times the derivative of e to the 2x. So it's 2x e to the 2x, which I'll write as c times 2x plus 1 e to the 2x. And now I have to differentiate again. So this is c times, I'm going to have v du dx, which is just 2 e to the 2x, plus 2x plus 1, that's u, times dv dx, which is 2e to the 3x, 2e to the 2x. And so this works out as c outside of 2x plus, 4x plus 2 plus 2. So 4x plus 4 e to the 2x. And now plug it into the original equation. Yp double prime minus 3yp prime plus 2yp equals, well, the second derivative is c, 4x plus 4 e to the 2x. The first derivative, well, we have to do minus 3 times the first derivative. So it's minus 3c 2x plus 1 e to the 2x, plus 2 times the thing itself, cx e to the 2x. And now let's simplify this. We have, in terms of x, we have a 4c here, minus a 6c, plus a 2c. And the x goes away. We have 0x e to the 2x. That's kind of nice. In terms of the rest of it, we have a 4c minus a 3c. And there's nothing from over here that doesn't involve an x. So it's going to be plus c e to the 2x. And that is supposed to equal 7e to the 2x. And notice how this came out to be a 0. If it wasn't a 0, we'd be in big trouble, because there's no x e to the 2x on the right. But as it happens, bye-bye, and c equals 7. So that's very nice. So that means that the solution is just yp is 7x e to the 3x, e to the 2x. So y is yh plus yp, which is a e to the x plus b e to the 2x plus 7 e to the 2x. 7x e to the 2x. No, it's a e to the x. Look at the original homogeneous solution on that board. One of the solutions was lambda equals 1. So you do get an a e to the x. The other one was lambda equals 2, which necessitated the extra x in there. Another question.
How did you know it was an x, not x squared?
How did I know it was an x, not an x squared? Well, I only needed an x because there was only one conflict. But I will show you the beginning of another example that I work fully in the book of where you'd need an x squared. So if you had, for example, y double prime plus 6y prime plus 9y is equal to e to the minus 3x, say. I work this out in section 30.4.5. This is this resolving conflict section. If you solve this, the characteristic equation has solutions minus 3 and minus 3. So you'll find that yh is equal to a e to the minus 3x plus b x e to the minus 3x. That was just the standard method. Now, if you take the right-hand side and you try to form a yp, you might want it to be a e to the minus 3x. That's no good because there it is. Well, actually, we'll call it c. So I cannot make this, so I have to put an x, but that's no good either because it's already here, so I actually have to do an x squared. Right, so the answer to the question is you only put an x squared in if you're doubly bad, if you've already used up the one with the x. But that would only happen if you had a double root there. All right, I'm nearly out of breath from all this stuff. I'm also nearly out of time, but I have to tell you one more thing about this in order to complete the whole sort of methodology, and that is how to deal with initial value problems. Now, I've left this to the end because remember, to do an initial value problem, you more or less, well, you basically have to solve the differential equation first, and then plug in the boundary values to find the two constants that are always left over, the a and the b. They always come out. So what I'm going to do is just show you by example how to find the constants just by more or less plugging in the conditions. Not even more or less. I keep saying more or less. I'm just going to do it. There's no more or less about it. Hopefully I get it exact, in fact. So, all right. Here is an example of an initial value problem. Which one do I want to do? I want to do the easier one because I'm getting tired. Okay. Y double prime plus 6y prime plus 13y equals 26x cubed minus 3x squared minus 24x. So there's the differential equation. But I'm going to give you that y of 0 is 1. And because it's a second order equation, I need another condition to tie it down. Two constants, so I need two equations. The derivative of y at 0, I'm going to say, is 2. So those are the initial conditions. So that's an initial value problem. So we start off exactly as we would, just ignore the initial values, ignore the right-hand side, in fact, form the homogeneous form. Y double prime plus 6y prime plus 13y equals 0. Okay, this is actually not so easy now that I think about it, but what can we do? We have 10 minutes, and we're just going to do it. So here goes. This has solution. Y is minus b plus or minus the square root of b squared minus 4ac. 36 minus 52 is 16. Again, the square root of minus 16, which is 4i. So this is minus 3 plus or minus 2i. That's how it works out. So the homogeneous solution, remember the method, it is e to the minus 3x, you take the real part, and then the constants are a cosine 2x plus b sine 2x. So that is the homogeneous solution. Now, what about the particular solution? Well, the right-hand side is a degree 3. It's a cubic. So my guess is yp is ax cubed plus bx squared plus cx plus, okay, what the hell, I'll allow a d because it's just by itself. It's not d of anything. Okay, so that's my guess. Easy to differentiate, luckily. 3ax squared plus 2bx plus c. And the second derivative's not so bad. 6ax plus 2b. Now I need to plug this in to the differential equation yp double prime plus 6yp prime plus 13yp equals 3 lines. Second derivative is 6ax plus 2b. 6 times the first derivative. 3ax squared plus 2bx plus c. I'm only using 2 lines. Plus 13 times the original ax cubed plus bx squared plus cx plus d. Okay, expand and group in terms of coefficients of individual individual terms. 13ax cubed. The x squared term will give me a 13b, but it will also give me a 18a x squared. The x term, I will have a 13c from the bottom line. I will have a 12b from up here, and I will have a 6a from over there. And finally, the constant term is 13d plus 6c plus 2b. All right, so that is just an expansion and a contraction all in one go. Hopefully I didn't make too many mistakes. And this is supposedly equal to 26x cubed minus 3x squared minus 24x according to the problem. So if we equate coefficients, we will have 13a equals 26. We will have 13b plus 18a equals negative 3. We will have 13c plus 12b plus 6a is equal to negative 24. And finally, this constant coefficient, 13d plus 6c plus 2b equals 0. And this is a collection of simultaneous equations, which actually is not so bad. A equals 2 from the first one. And then you get 13b is negative 39, so you find that b is negative 3. Plug this in, and you get, what do you get? 6a is 12, 12b is minus 36, plus 13c is minus 24. And so you find 12 minus 36 is actually negative 24. So I believe c equals 0. And in here, 2b, 13d equals 6. So d is 6/13. So if I'm not mistaken, yp is 2x cubed minus 3x squared plus 6/13. And I intend to check this, because working stuff out on the board in a hurry is never very reliable. Yes, that seems to be what I got. Okay, so over here then, I'm going to write down the complete solution. Y is yh plus yp equals, well, the homogeneous piece is e to the minus 3x, and I'll write it like this. A e to the minus 3x cosine 2x plus b e to the minus 3x times sine 2x plus the particular solution, 2x cubed minus 3x squared plus 6/13. All right, that's not so bad. That is the solution to the differential equation. Right, the homogeneous plus the particular. Now, unfortunately, we have an initial value problem. It's unfortunate because we have to do more work. Now, one thing we know immediately. We know that y of 0, we're given, is equal to 1. So put x equals 0 and y equals 1 and see what we get. So you get 1 equals a e to the 0, which is just a. Cosine of 0 is 1. So you just get a. On the other hand, sine of 0 is 0, so that term goes away. This is 0, and this is 6/13. So we've already identified that a is equal to 7/13. Unfortunately, y prime is trickier, and you have to differentiate this to find out. See, we want to use the condition that y prime of 0 is 2, which is all the way up there on the top right of the board. We don't need to focus on it now. Y prime, I'm afraid, we just have to differentiate this. So we're going to have to do one last product rule pair. You get a outside of, actually a is 7/13, so we may as well replace it. Outside of e to the minus 3x times the derivative of this. Actually, I'll do cosine, so it's minus 3e to the minus 3x times the cosine, plus, although it will be another minus, 2 from the cosine, e to the minus 3x sine 2x. All right, that's the A piece. Plus the B piece is minus 3e to the minus 3x times sine 2x plus 2e to the minus 3x cosine 2x. And that's the B piece. And now I have to differentiate the rest. Plus 6x squared minus 6x, and then the other piece goes away. So what I've done is I had the answer for y. I plugged in 0 first to get a, but I still need to find out b. So I have to differentiate y and find an expression for y prime. Now, y prime of 0 is 2. So this means that put x equals 0 and y prime equals 2. So this mess of equations simplifies considerably to 2 equals, okay, again, when x is equal to 0, this sort of term is 1 times 1, and you get minus 21/13 from that. And the sign goes away. And here the sign goes away. And this is a 1, so you're going to get plus 2b. And actually, x equals 0, so both those terms happen to go away. And that's the complete equation here. 2 is 26/13, so what is this, 47/13? So b is 47/26, unless I made a mistake. And now let's see if that's right. Yes, I believe it's right. Okay, so we found a is 7/13. We found b is 47/26. So now I just plug those in here to get the final solution. Y equals a is 7/13. 7/13 e to the minus 3x cosine 2x plus b, yes, 47/26 e to the minus 3x sine 2x plus 2x cubed minus 3x squared plus 6/13. And that is the solution. Now, before we finish, let me just say that I had to miss out section 30.5, which is on modeling using differential equations. Bless you. I have only one example in there, but you should read this example. They do ask problems like it. And I just didn't have time to do it. I can go through it in the reviews before the end, but certainly this won't be on the video. So, since this is the last video, and you see I dressed up a little bit for the occasion. Well, I just happen to be wearing this, but anyway. I hope that this has been, at least on the video, and of course in the classroom as well. We have 4 more sessions, as you know, reviewing the course. But from the point of view of the video, I hope this has been useful. I hope that you can look back on this and not think of it as a total waste of time. Hopefully you've learned something. I've enjoyed doing it, and hopefully it goes well with the book, and you can mix and match as you see fit. If you do have any comments, adrian@calclifesaver.com. I would be very happy to hear them, but I don't think I'm going to redo these videos. So, with that, thank you very much.